To the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our first lecture covering material from Chapter 6. We begin this lecture looking at this diagram that's showing gamma rays. You might not be familiar with that symbol, but this little symbol here is gamma rays, X-rays. You probably heard of these. UV. We've got visible, very small, infrared, microwave, and then we're on to some different types of radio waves. You'll see the radio waves make up a large proportion of this diagram. Now, we call these we call this the electromagnetic spectrum, and these are all waves. Even though some of them say rays or UV, it doesn't really imply that it's a wave, but they all have a wavelength. And the wavelength is down here at the bottom, and it's represented with this lambda symbol. It's measured in meters, and we can see that the radio waves are the longest of the waves on this scale, and the gamma rays are the shortest. And you might also notice that there's an energy component at the very top. So energy is increasing toward the left. So our small wavelength has high energy. Now this symbol up here is the Greek symbol mu, mu. And it kind of looks like a V, or sometimes I draw it like a little funny U. Units are hertz, and we'll talk about hertz in a second. But what I want you to see now is that with the frequency, the larger the frequency, the more the energy. So this is different than the wavelength. We've got an inverse relationship here between frequency and wavelength. The next thing we did in the lecture was we did a little demonstration using just a household propane torch, and I had a series of chloride salts, and we chose all of these to be chlorides because we wanted to note any differences that we saw, and we could say that it must be the cation or the metal that's contributing to these differences. And what we saw was that these different salts burn different colors, and some of them are quite spectacular. So once we looked at each salt and wrote down our observations, I was able to pick 3 randomly, and the class was able to identify them just based on the color. So this is a nice method for identifying cations as they're being burned, and it's just really pretty fascinating that the colors are so much different. And we're going to ultimately learn why these colors are different. So a couple key points just based on our observations we have noted on this slide. We talked about how fireworks will use these different salts. This is a great image showing you the different metals that can be used to produce different colors in our fireworks. So you've seen this before. So light is an electromagnetic wave, and all of these waves travel the same speed, and it's called the speed of light. The size of this is quite big, 2.998 times 10 to the 8th meters per second. That's really, really fast. Sound travels at about 300 meters per second, much, much slower. Now remember, light is the entire electromagnetic spectrum, not just the visible region. So a gamma ray will travel at the same speed as a radio wave. They have different wavelengths, different frequencies, but they travel at the same speed. So at the bottom, we talk about the wavelength. There's that lambda symbol. And the units are typically in nanometers because most of these wavelengths, especially in the visible region, are pretty small. So the nanometer makes a nice unit, but you're going to want to be able to convert from nanometers to meters in both directions. We've got the 2 factors here. You can pick your favorite factor and just be comfortable doing that. We'll use that a lot in this chapter. Now the frequency, this is the symbol mu, and I'm not sure if that V is really accurate for the symbol, but it's the best we could do. Units for this are hertz, Hz, and you've probably seen this before, like on a fluorescent light bulb that they'll say like 60 hertz or 60 Hz. You might have seen this before. And what the hertz is, the units are the same thing as 1 over seconds or seconds to the -1. So what it is it's like cycles per second. And when we're talking about waves, we talk about waves per second. So this is just showing like how we have different wavelengths. This is just a visible light. The red has the largest wavelength, and we can measure this from any 2 points that are the same on the wave. So I chose the apex on the red, and I have 3 waves here. And what we said is this is like a snapshot. It's like 1 second in time. And if this were the case, and it's not, but if it were, we'd see 3 waves in 1 second, and from the red, where the violet, we'd see 9 waves in 1 second. So that corresponds to 3 hertz for the red. That's our frequency. And we have 9 hertz as a frequency for our violet. There's a relationship between the speed of light, the frequency, and the wavelength. If we multiply the frequency by the wavelength, we'll get the speed of light. The important thing here is that our units of wavelength are in meters. Frequency is 1/seconds, so when we multiply the two, we get meters per second. The speed of light will be given, although you'll probably have it memorized after doing a few practice problems using this. So make sure your wavelength is in meters. This is where you might need to go from nanometers to meters. So here's an example. I've got a wavelength in meters, and I want to solve for the frequency. So I can rearrange the equation and say that it's the speed of light divided by the wavelength, and canceling my units, I end up with 1/seconds, and that's hertz, and I have a frequency. We also show going from nanometers to meters and then doing the same calculation, solving for frequency. So light has a duality, and the short story is light acts like a wave. We've seen that. It has a wavelength and a frequency, but it also behaves like a particle. And the particle phenomena is explained by the photoelectric effect. And we're going to make a separate video talking about the photoelectric effect. But for now, let's just say, okay, matter or waves, light can act like a particle and it can act like a wave. It's got properties of both. So we can calculate the energy of an individual photon of light. And this goes back to the photoelectric effect, where we say that light, when it's acting like a particle, it's like an individual little bundle of light. And we call that little bundle a photon. So when we talk about a photon, we're talking about light, but just one little bundle of light. So we've got this formula, E of a photon, energy of just one photon, is equal to Planck's constant, that's a new constant, and this will be provided, and times the frequency. So the Planck's constant has units of joules times seconds, and frequency we know is in hertz. So remember that we said the speed of light is equal to the frequency times the wavelength. Well, we can rearrange this formula so that and solve for frequency, which is the speed of light over the wavelength. So I can replace frequency in this formula, the energy of one photon, with speed of light divided by wavelength. So if I had a wavelength and I wanted to calculate the energy of one photon, I could use the formula hc over lambda, h being Planck's constant, c being the speed of light, and lambda being my wavelength, has to be in meters. If I wanted to calculate the energy of a photon from a given frequency, I would just use E equals h times mu, or over here, and this is my frequency, Planck's constant, energy of one photon. That about sums up our first lecture on Chapter 6. Thanks for watching. Give the video a thumbs up and subscribe if you'd like to see more of these mini lectures on the Professor's DuBois channel.